Caramel. Artificial intelligence-based cybersecurity for connected and automated vehicles. Some of the damaging effects of cyberattacks to an industry like the Cooperative Connected and Automated Mobility (CCAM) are material damages, the reputation of vehicle manufacturers, the increased denial of customers to adopt CCAM, and ultimately, the great danger for human lives. Caramel is aiming to deal with modern cybersecurity gaps through the use of advanced artificial intelligence techniques. The three pillars of Caramel are autopilots, V2X communications, and electric charging. Attack on sensors. These attacks do not require any physical access to the vehicle or tampering with the communication system. Attacks via data and interfaces. V2X applications interconnect not only vehicles but also infrastructure and pedestrians, hence it is critical to protect V2X functions from a misuse. Attacks via e-infrastructure. Unauthorized access and control of EVSE stations and firmware modifications should be prevented at all cost. How to address all of those scenarios? Artificial intelligence techniques will be used to model cyber threats, detect cyber attacks and to identify appropriate responses for each of the main pillars addressed by Caramel. An anti-hacking device will be trained using machine learning techniques. Once deployed, will disable higher-level functions in case of a cyber attack. How to address
Hello everyone, sorry for the delay for today. Now, for this second OEM and Partners Workshop from the Caramel project, Jordi Harry speaking, this project coordinator. And let's start with the agenda of today. Okay, I'm checking about 34 participants for this workshop. It's a very good news to start with the workshop. And all the panelists are prepared. We have an agenda, an amazing agenda to go in detail with the first outcomes of this project, this H2020 project. And let's see how to introduce. We are happy that you are interested in our activities, and only to remark about this workshop and how we want to run the different activities. We have, a webinar. You are an attendees. You can use the chat. You have any questions, we will catch all these questions during the session and go forward with the different panelists. Okay. Let's check the agenda for today. Okay. Okay, for this, only to remark that we have a specific hashtag H2020 Caramel. If you can use in the different social networks, we will be happy that you use this. And for the agenda for today, we have this welcome, and to check the agenda. At the first panelist, we have our technical coordinator, Peter Hoffman. We have a specific overview of the project and to introduce to our activities. And after that, we will go with the different pillars that we are covering from the project. First, from our trial work package leader, Petrus Kapsalas from Panasonic. We will go with the autonomous mobility topic. After that, we will go with one of our Korean partners, Katek, Mr. Choi, with a remote control vehicle. This stage, we will go with a BreakTime for 15 minutes. And after that, we can continue with a connected mobility slot with Jordi Casademont from E2CAT. And of Caramel with Electromobility with Bob Ilders from Flux. After that, we will have a roundtable and some conclusions, questions and answers with the audience. And we have some extra invitations that I can present here. Only we have Jesus from our advisory board, Christos from the NBOE project, Alejandro from IDIADA, and Peter Hoffman and Petrus Kapsalas from this Caramel projects. Okay, but let's start with the first stage of the agenda of today. Okay, and let's go with Petrus. With Peter. Sorry, I think that you can share.
Yeah, hello.
Hello.
Maybe you can take over now.
Yes, I'm trying to.
So just a moment. So it seems to be that I have to actually
Yes. Now
rejoin. Sorry.
But I think that now you can.
Yeah, you know, I'm using Mac OS, and so I will rejoin in a moment. Sorry, it's the first time I'm using the Zoom client. No.
Okay, let's wait for Peter. Now. You are muted.
Well, there we go.
Now.
As you know, we are a security project, and of course, I'm using a secure operating system, and it doesn't allow me to just have an application like Zoom share the screen. No? So, yeah, no. So, but now you should be able to see my screen, and so let's go into the application. PowerPoint. Okay, I'm trying to give a very short technical overview of the project. Now that we had some delay at the beginning, it will be even faster, but that doesn't matter, no, because when it comes to the 4 pillars, we will have sections devoted to each of the pillars, 30 minutes each, and I think the colleagues will talk about very much detail. No? So maybe I will skip a little bit over these slides, no, to save some time and also save some repetition. So why are we doing a project like Caramel? No? So we are looking at the connected car, at the autonomous vehicle, a semi-autonomous vehicle, and these cars are actually data center on wheels. You could say they have lots of control units, little computers that run different applications. Of course, the most obvious is the entertainment system, but behind the scenes are a lot of internal buses. There are sensors sending the streets, the surroundings, the environment of the car. There are cloud interfaces. Nowadays, you have normally a cloud interface to the vendor cloud, to the car manufacturer. But in the future, there will be lots of different cloud interfaces where a car will be connecting to. If the CCCam environment actually takes flight. And of course, yeah, as part of that infrastructure, you have the vehicle to X infrastructure. Vehicle to X, the X stands for other vehicles, the roadside infrastructure, cloud interfaces, as I said. And of course, they are standardized protocols, they are standardized components, and they will be standardized attacks. And we try in the Caramel project to use machine learning to detect different kinds of attacks against the different kinds of entry points into the connected car. Yeah, that is a very high-level overview of the 4 pillars. The pillar 1 looks at attacks against the sensors that I talked about. Pillar 2, it's about the radio interfaces of the car against the vehicle to X infrastructure, the GPS location servers, and yeah, the OBU, the onboard unit, which is in our parlance, the communication device that is directly connected or implementing the radio network. Is the first entry point, maybe for an attacker. And the pillar 3, we look into the e-charging infrastructure. As you may know, e-mobility begin to accelerate the adoption of e-mobility, and of course you have charging infrastructure, and there could be attacks against the interface at the charging station or maybe abuse of the charging infrastructure. And yeah, also we have our Korean partners which look at the different aspects of the connected car, and I will look at that later in the later slide. Then there's a common element that's actually the one that we are as Deutsche Telekom Security as partner in the project are responsible for, and that is a specific kind of intrusion detection device that we want to bring into the vehicle. That is the anti-hacking device. And the anti-hack device, the idea is basically that it's connected to the internal buses, can look at the vehicle to X traffic, can look at the sensor data, and it is a passive device, so it does not really interfere with the safety and the operation of the car. Yeah, it's not meant to be an attack surface on its own, and you want to be able to implement on a daily basis or maybe hourly basis new detection algorithms, and something that you wouldn't be able to do in a normal control unit in the car. So it must have a high level of the security itself, and we implemented things like secure boot, secure firmware updates, and Docker container technology to encapsulate different detection algorithms. Yeah, I think that's a quite novel concept to have that in the car, a controller device that's actually devoted to enhancing the security and safety of the car. Now, I must look at the clock. Yeah, a very short look at the different pillars. Pillar 1, as I said, looks at attacks against sensors of the car. And yeah, if you're looking at the 4 pictures, the 2 on the top, for example, now they have a picture of people crossing the street, and yeah, it's correctly recognized by the algorithm on the right side. And then there could be specific kind of attacks that bring subtle perturbances into the picture. It could be a poster on the street, for example, or maybe a direct attack on the sensor data on the internal buses, and attackers use generative adversarial networks, also that is machine learning itself, to generate effective attacks against a specific machine learning based safety algorithm in the car. And we try to detect attacks like these. And there's a second part of pillar 1 where we are looking at specifically defaced traffic signs, which is a real attack, and there have been real cars that have been yeah, I say spooked by defaced traffic signs. There was a news item about the Tesla that thought it was actually 85 speed limit instead of 35. So that's a real world attack, and that has been shown in the wild. And we use actually training and testing pipeline that we have built in our lab to actually implement these kinds of attacks without having to build a real street with traffic signs. And we're using the color simulation environment to have a simulated city, simulated cars, and simulated defaced traffic signs. And we use machine learning to derive models that we then convert to something that is able to run on the TensorFlow Lite model on our anti-hacking device. So that's one of the anti-hacking devices that we're using. It's based on the Coral Dev board. Coral is a good company that uses the TensorFlow processing units and brings it into a low-level device, and then we test that. We connect the anti-hacking device to the real color environment and run the attack again and see if it can actually be detected. Now coming to pillar 2. Here actually we have an interesting add-on. So we not only look at the messages and if they contain some sort of attacks, but we also have an interoperability scenario that we integrated into the project, that we have roadside units, which are the infrastructure part of the vehicle to X communication. And we convert between cellular CV to X and 802.11p, which is a Wi-Fi based vehicle to X technology. And this is basically, they use the same radio bands, but they are incompatible on the physical layer. And we are using multi-access edge devices as roadside units to make a conversion, so that we have actually the same logical layer, the same protocol layer, but the different physical layer. And so actually these cars that use different technologies can talk to each other. And of course, we can also use the edge side units, the MAX, to look into the protocol messages, detect attack patterns, revoke certificates, and so on. And we will hear about that later on in the pillar 2 presentation. So maybe because of time, skip that. Then going to pillar 3, that is about attack on the e-charging infrastructure. We have a partner Greenflux that runs a large network is connected to a large network of charging stations, and they actually basically run the multi-purpose back office infrastructure, and they're in a good position to look at these charge data records and detect large-scale attacks against the e-charging infrastructure. And you could imagine if there's maybe a coordinated attack that could lead to fluctuations in the electrical grid and maybe even to outages. So that's attacks that as more and more e-mobility, e-vehicles come online and are currently at this charging station, that becomes a real threat to the national grid infrastructure. And we also use machine learning to look at these patterns, detect attacks, and propose possible countermeasures. So now, last but not least, our Korean partners, they have, and we have actually 3 Korean partners which have a slightly different focus and different sub-projects. They are looking at the vehicle gateway and remote controlled vehicles, and also have a cybersecurity module that's based also on machine learning or artificial intelligence. And the machine learning based intrusion estimation algorithms. So what our Korean part is doing is actually a good fit to what I've presented for the previous pillars, and because it's we have 3 partners, and I think it wouldn't give them any service to try to do that now in 1 minute. And we have a pillar 4 presentation for 30 minutes later on, and you will get to know much more about the details about these approaches. Yeah, so that was a very short rundown of the Caramel project. I don't know if you have any questions at this stage, but as I said, there will be for every of the 4 pillars individual presentation later on. This time for Q&A. Okay.
Okay, thanks, Peter. Seems that through the chat there is not questions, and only to share with you because before we have some issues, is about the agenda. Now we saw an overview from Peter, thanks, about the project, and now it's time to go with Petros with autonomous mobility. After that, with Jo-Chun Choi from CATEC. Okay, before the break. Please, Petrus, you can go on. Stop sharing.
So, wait a minute. Yes. I guess that everybody can see my screen, right?
Yes, not in presentation mode, but
yeah, I guess now it's fine.
yes.
Okay, so hello all. Thanks a lot for joining the second Caramel workshop. I'm Petros Kapsalas. I am the technical leader in Panasonic Automotive, and in Caramel, I am representing the Pillar 1, which is related to the cyber attack and detection and mitigation on the sensing level of the autonomous vehicles. This issue is a quite hot topic for the automotive community because we can have cyber attacks on multiple sensors, and then the question is, how can we use the multiplicity of the sensors in order to detect and mitigate the cyber attacks? So the goal of Caramel is to design and implement detection and mitigation techniques which are based both on deep learning as well as on multimodal fusion, and take advantage from both sparse and deep priors in order to detect and mitigate the attack. And the evaluation of the detection and mitigation engine is happening at the twin layer. At first at the viewing layer, and at second at the perception layer. The viewing layer is what the observer can check through visual inspection, while in the perception layer we are using specific KPIs measured, which check how the detection rate is affected before and after the cyber attack. We are using deep learning technologies for threat intelligence and anticipation of cyber attacks. The data that are being used and tested in Caramel come from from a multimodal setup of sensors. So we are considering data coming from cameras, from ultrasonics, from GPS, and from LIDAR. The data that are being collected are heterogeneous, and we are using different sensors in order to check how one can act as a complement of the other in the detection and mitigation engine. There are multiple challenges that need to be addressed. The challenges are mainly related to handling missing data, to handling unsynchronized data, to handling noisy data, and also to identify and suppress all these outliers before the data are fed to the neural network, which will assess the occurrence and will mitigate the attack. In this slide, I am illustrating the vehicle that has been engaged for Caramel. It's a vehicle that accommodates a multitude of sensors, including the GPS, LIDAR, cameras, ultrasonic sensors, differential GPS, V2X, and also a central computing unit. The expected outcomes of Caramel are summarized in this slide, and it mainly consists of establishing a PKI-enabled vehicle identity management system. We are also exploring solutions against cyber attack detection on machine vision systems. We are using situational awareness based on a multitude of sensors in order to check how the complementarity addresses the issue of detecting and mitigating the attacks. And also we are proposing some fallback actions for minimal risk in order to enhance the safety indexes. So an overall architecture of the software that has been developed in Caramel project is summarized in this slide, we have data that are fed through a data augmentation, through an offline data augmentation, which consists of synthetic data, real data, and the augmentation of synthetic with real. This is this pipeline over here, and also we have some real data which are captured from the vehicle that is engaged for the project. Now, once the data is collected, either from the synthetic data branch or from the real branch, there is a noise suppression and data handling engine that appears on the top of the pipeline. So the synchronization and the missing of data is addressed at first, and then the noise is suppressed. And some types of cyber attacks are also detected in this layer, and after this, there is a cyber attack detection and mitigation engine, which is based solely on the perception layer. So at this stage, the attack is assessed based on the scene understanding. For example, if a traffic sign, the traffic sign is detected, interpreted, and the anomaly is detected there. Or we are using some robust machine learning modules in order to reduce and remove the attack on the perception layer, while here we are on the signal layer. So we have two layers of detecting and mitigating the cyber attacks. Finally, we have a decision fusion module, and the output of both comes to the comparison and evaluation, which, as I have described earlier, can be either through visual inspection or through the quantification using some KPIs. So the types of attacks that we have considered in Caramel can be distinguished into two broad categories: the internal attacks and the external attacks. In the internal attacks, we are considering attacks in the camera sensor layer, which can be either deterioration of image quality or adversarial attacks. While in the external attacks, we are considering physical-based adversarial attacks and attacks on the traffic sign. This means attaching a sticker on the traffic sign or a graffiti or whatever in order to intervene in the scene understanding. Now I'm going to give you some summary of how the cyber attack detection and mitigation engine looks like, and which are the type of deformations that we can capture, and what kind of output we get in Caramel. As we said, we are considering adversarial noise suppression using deep restoration networks. These networks have been designed in order to be robust across a number of transformations, both morphological and geometric. So you see here, for example, that we have some adversarial noise attack based on adversarial noise on a daytime image and on a nighttime image, and on the row below you can see which is the output after the cyber attack detection and mitigation engine has been applied. You can see that through the visual inspection layer, all the adversarial noise has been removed, and the viewer can understand that the scene is perfectly restored. While at the perception layer, we are investigating the output of the mitigation engine through inspecting the segmentation map of the scene. Here we have the original image without any cyber attack, and on the mid row we have an attack which has been performed, and on the row on the right we have the output of the mitigation engine. You can see that after the image has been attacked, the attack is also apparent in the segmentation map. The borders of the boundaries of the objects have been distorted. We have ambiguous areas which are represented here as black regions, which do not exist on the image on the left. So you can see that the cyber attack has caused a disturbance of the segmentation map. But after the deep restoration network was applied, the attack has been mitigating, and this is obvious if you compare the segmentation map from the right and the left column. Another instance of the attack, another instance of the operation of the mitigation engine is can be seen here. The noise here is removed. The noise removal takes place using a deep neural network. You can see again how the original image looks like and how the segmentation map of the original image looks like, while the original image is being attacked with noise of specific models. Here can you hear me?
Yes, Petros.
Okay, sorry, because I thought that I had a network issue. So here you can see, here we have been experimenting with different types of models of noise and their effect in the output of the segmentation map. And on the bottom row, we show how through the deep neural network we can clean the image. And then how the segmentation map converges with the original one. In this case, we have a close to perfect mitigation of the attack. As I have already said, the data are fed both through Carla and through real data. In this slide, I show you an instance of the pipeline of the architecture. The attack is performed stochastically on the clean image, and then the image is passed through the convolutional neural network on this side through the convolutional autoencoder for image quality restoration, and then the image is denoised. And here we have a different type of noise. It's not like visible by the viewer, but it's an adversarial noise that affects the segmentation. You can see here, for example, that we have a noise attack which is not visible by the human eye. However, on the perception of the scene, it is visible. And then on the final image, we can see how the restoration has been performed using the deep neural network architecture. We have been experimenting with different types of restoration mechanisms. We have the two-stage extension, the two-stage fully connected neural networks. We also have combined the drive guard with parallel detection stream, the drive guard with SVM, and the drive guard with linear classifier. And we are reporting that the total accuracy is in all cases above 97%, and the frame rate is quite real time in all cases. So these are some of the methods that have been used in Caramel for noise removal. In general, the pipeline for adversarial attack detection and mitigation consists of a pre-processing stage and then a robust segmentation stage where we have implemented neural networks which are robust in segmenting the image in the occurrence of specific adversarial attacks. Above from the degradation on the image quality and the adversarial attacks on the image layer, we have also considered attacks on the physical layer as a traffic sign attack. the solution in these cases looks like how it is presented in this pipeline. We have some scenes with traffic signs. The traffic signs are detected and then they are cropped. Then we have a pre-processing unit after the cropping, and the cyber attack detection and mitigation for the traffic signs consists of 3 stages: the anomaly detection, the robustification, and the recognition. In the anomaly detection, we get the cropped traffic signs, and then we check whether an anomaly is occurrent or not, occurs or not. In case that there is an anomaly detected, then we have a robustification data where we have the reconstruction and the generation of meta traffic sign data. While in the case that no anomaly is detected, we have the traffic sign recognition model, which gives the output of the metadata. Here we have also measured the accuracy and the runtime of these techniques, and it seems that for the recognition, the model accuracy is close to 99%, and also the accuracy of the anomaly detection and recognition and reconstruction engines are also quite high, are above 90%, which means that even in the occurrence of an anomaly in the traffic sign, we are able to reconstruct and mitigate with an accuracy rate of 91%, and the frames per second that has been measured in an NVIDIA RTX is like 251.82 milliseconds. Except for the deep learning based approach for the cyber attack detection and mitigation, we have also employed unsupervised variational approaches and approaches based on multimodal fusion. The unsupervised variational approaches that we have used for noise removal are trying to implement some physical models for noise suppression, and these are basically related to allow diffusion only in some specific directions in the image and without disturbing the edge content, because we know that the edge and the high frequency features in an image are very important for the classifiers. So you can see here that the anisotropic models that we have considered do allow diffusion on smooth areas, but don't allow diffusions on across boundaries. So we allow intra-smoothing but not inter-smoothing in order to preserve the edge content of the image. Here I am presenting some of the visual inspected output. As you can see on the top row, some original images, and then attacks on the original image with specific noise models, and the output of the restoration. In all cases, you can see that the noise has been removed. However, the edge content and the intensity content of the image has not been disturbed, which means, as I will show you later, that the perception is not affected. So for this type of unsupervised mitigation and detection approaches, we are inspecting the results also on the perception layer. What you can see on these images is the top view of the occupancy grid map before and after the cyber attack. Before and after the mitigation of the cyber attack. So what you can see as red dots are the boundaries of the objects as they are detected at the occupancy grid map before the cyber attack. And on the 2 consecutive layers, you can see how does the occupancy grid map looks like after the cyber attack. is mitigated with two different techniques. The videos will be available after the presentation. For this case, we have considered some key performance indexes in order to quantify the output of the mitigation engine, and the KPIs are basically related to measuring the distance transform of the boundaries of the objects before and after the mitigation, and also the intersection over units between the objects before and after the mitigation of the attack. Here I have, we are going to present some output of the videos that are related to mitigation for adversarial attacks. I guess that you cannot see it, but I will share the videos later. Now, except for the camera, except for the deep learning based approaches, we have also considered the other sensors for mitigating the attacks. In this case, we are using the LiDAR in order to mitigate the attack that happens on the image, on the camera. We have trained deep neural networks using point clouds of objects detected through the LiDAR. We project the 3D object to the image plane, and then we correlate the two outputs to provide improved situational awareness. So I think now, if it's okay, I will share with you the output of the videos. Jordi, we have time to.
Yes, you can go ahead. You have 3 minutes, 5 minutes. But we cannot hear you. As a reminder, if you have any question, you can use not Petros. We cannot hear you. You can use the chat if you have questions from the audience.
Sorry?
Now, yes.
Yeah, I don't know what happens. I guess that the network is really bad for this. So
if not, you can try later, or you can do a reference that we have a specific YouTube channel of Caramel. Some of the videos are there.
Yes, that's correct. I can show you some of the output. I don't know how much our network will allow to do it, but
now, yes.
Okay. So now you can see, for example, on the top layer, you can see the output before. You can see the scene generated by Carla without any attack, and then after the attack and what is happening with the reconstruction and the segmentation map. So you can see here. So you see that even when the image is attacked, we are able to reconstruct the scene and remove the segmentation map to be eliminated. So you see here that we have stacked lines introduced, but still the output image is reconstructed, and we have not has not been affected, and also the output of the segmentation engine was not affected by the introduced lines. All these videos are going to be made available through our Caramel channel. I think I am okay.
Okay, thanks Petros for this, for the autonomous mobility pillar, this pillar one from Caramel. And checking if there is, yes. Here, Petros, we have a specific question from Jonathan Petit about the drive word. You saw that 98% of accuracy. Should we get more? What is the acceptable target accuracy for the perception system?
Actually, thanks a lot for the question. Actually, what we have reported as accuracy is the accuracy after the mitigation of the attack. So 98% was the accuracy that has been measured in the given data set. I think, given the fact that the cyber attack detection and mitigation is a very new concept in the automotive, as far as I know, there are not specific requirements for the accuracy on this topic because it's still a research topic. This is why Caramel has been funded as a project to investigate these topics. From our experience, I think that an accuracy that is above 95% is a quite high accuracy for cyber attack mitigation, given the fact that this area of research is a quite new area of research.
Okay. Okay. Perfect. Let me appear another question. If not, we can go with the next pillar. It's about the remote control vehicle with Mr. Choi from CATEC and the rest of the Korean partners. Thank Petros.
You're welcome.
Okay. Mr. Choi, are you ready?
Okay, so let me share the screens. All right. So can you see the screens?
Yes, not in presentation mode, but
okay. Let me check. Oops. Is it okay to go ahead with
yes,
this?
we can go with this.
Okay, sorry for the. All right, so good afternoon. I'm Yujun Choi from CATEC, and Dr. Taesang Choi from H3 is here with me for sharing the Korea partners achievement with regard to the cybersecurity of remote control vehicles. So, so just before starting these sessions, I would like to share that since the Korea partners joined the Caramel Consortium almost 1 year later than the EU partners, so our result is quite behind schedule than the EU partners. So please understand our achievement, and we hope we will speed up our achievement to align the with the European partners. So let me first explain what is the remote control vehicles. So remote control vehicle is the vehicle that is teleoperated by the human operator from remote site with reliable connectivity between the remote control vehicle and remote servers. So the vehicle gathers the huge amount of the data through the every sensors, such as the lidars, radars, or camera sensors that is mounted on the remote control vehicles, and sharing it with the central ITS station or roadside ITS stations and with each other. So stable and robust VTX connectivity must be secured to not only real-time sharing of the vehicle status and sensing data, but also vehicle control data. In the remote control vehicle applications, the uplink data rate is more important than the downlink data rate because of the uplink data contains a huge amount of the sensing data, while downlink data contains only the control data. So the Japan proposed the remote control vehicle related work item recently in the ISO TC204. It is defined the remote control vehicle application that should be used to the ODD extension use cases, such as the restarting after stopping on the shared AT stations, and the remote support when out of ODD due to the rain, fog, or the sudden weather changes, and joining the priority road from side road, no traffic lights, and extras. And the 5G AA also defines the several RCV related use cases. The first one is the infrastructure-based teleoperated drivings. And in these use cases, they are defining the service use cases, like user stories like this. So when the automated vehicle detects a failure in a critical subsystem, it prepares a status report and using its positions performs the necessary safety functions. For example, the slow down or stops, and transmit all the information to the remote operators. And assuming the instance location is covered by the infrastructure sensors, for example, the camera sensors and radar sensors, etc., the teleoperator retrieves a real-time image data of the road environment centered around of the remote control vehicles. So based on this perceived the situation and the capabilities of the vehicles, the remote driver can provide the appropriate trajectory and maneuver the instruction to help the remote control vehicle move to the safe locations. And second one is the teleoperated drivings. So in these use cases, the temporary health issues, for example, the illness or headaches or sudden heart attack of the human driver impairs his concentration, reactions, and the judgment, and consequently affect his ability to drive safely. So the driver of the vehicle asks the remote driver to take control of the vehicles and drive the vehicle in an efficient and safe manner from the current location to the safe destinations. And another one is the teleoperated driving for automated parkings. So in these use cases, when a vehicle arrives at the destination parking area, the driver leaves the vehicle and it is parked by the remote driver located in the remote control centers. And last one is the teleoperated driving support. So in this use case, in the remote control vehicles or automated vehicles may detect highly uncertain situations and cannot make the appropriate decision for safe or efficient maneuvers. So in this case, the automated mobilities or vehicle can ask for the support of a remote driver in order to resolve the difficult situation and then switch back to the normal autonomous driving mode without the remote driving support. So as I explained so far, the remote controlled vehicle can be used in various situations. And from now on, I'm explaining our implementations. So as you can see in this slide, the control input, such as the steering wheel angles or linkers and axle or the brake pedal positions are generated by the remote control station that is developed using the real automotive ECUs, such as the body control modules or engine control modules, while the vehicle status data, such as the vehicle speed, RPM, or fuel levels, and extras, are acquired by the remote controlled vehicles by the access to the in-vehicle network directly. And the control and status data is shared through the wireless communication link, for example, the DSRC or the millimeter wave or 5Gs. And since the real automotive ECUs are used both remote site and the remote control vehicle site, the outlier or the error data can be more easily generated by the software for testing and evaluation of the Korea use cases. So this slide shows the implementation of the remote control station based on the millimeter wave communications. So you can see the left figures, the vehicle they call the remote control station is we keep the millimeter wave, the networks and the base stations and remote control stations. So as you can see in the bottom left figures, so we are using the real automotive part to generate the control data to be sent to the remote control vehicle via the millimeter wave communications to control the remote control vehicles. And from the right side of the figure, you can see the test vehicles, and in the vehicles we can access the in-vehicle networks through the CAN gateway, and all the vehicle status data, for example, the speed, RPMs, and fuel levels and extras can be gathered through the CATEC gateway, and all the data can be transmitted to the remote control center through the millimeter wave communication link. And also the CATEC gateway that is developed to access the in-vehicle network of the tested vehicles is is sent of the control data to the in-vehicle networks, so that the vehicle can be controlled by the teleoperators from the remote site. So from now on, the Dr. Taesang Choi from H3 will explain about the AI-based cybersecurity algorithms and achievement. So Dr. Taesang Choi, are you ready to present?
Yeah. Okay. Thank you. We both are Choi. Last name is Choi. I'm Taesang Choi from H3, and H3 is responsible for developing the cyber attack solution for RCV vehicle and its associated environment. And this slide shows two requirements and scenarios for the cyber attack and how we can develop scenario to handle those potential cyber attacks. The first one is attack on RCV control and status message transmission. As Dr. Choi previously described, there will be a control and the response status message communications between RCV and control center. So we need to protect any cyber attacks for these important messages. Okay, yeah, could you move on to the next one? Another attack scenario, requirement scenario is an attack on RCV status image transmission. The message exchanges between RCV and the control center can be either text-based protocol messages, or it can be the status images, which has been captured by various sensors of the RCV. And we also have to protect attacks on those status images between the two entities. And currently, yeah, as he mentioned, we initiated this project later than EU partners, and we are working on the solution for the first attack scenario, which is the text messages between RCV and control center, and we'll tackle the status image transmission attack later on. But so for this presentation, OEM workshop presentation, we will describe our initial effort on the first requirement scenario. So please move on to the next slide. So in order to detect any potential cyber attack of the messages between RCV and the control center, we propose the following the system architecture. We considered the messages between RCV and the control center as a series of packets, and which will be converted into a flow. So a flow is a set of packets between RCV and control center, which compose a particular session. And then we capture the packets, and then we extract, we combine those packets into a flow, and then we extract payload part of that set of packets within a flow, and we try to convert those text data into an image, and then we use this image as an input data set for CNN-based training. So we train them using this CNN model that we have developed, and then based on the trained result, we generate a model to validate unknown, untrained data sets, so that we can identify which one is normal messages between RCB and the control center, and which one is the attacked one. So that's a brief introduction on our solution system architecture. And could you move on? I will go into a little bit details for each. So in order to extract flow payload and then convert that into image generation, we use the size of 784, which is 20 by 28 payload values of flow with packet, and then extract those payload values up to 784 in order to match the size of MNIST image. We use a modified NIST database image to convert the payload into the image, and each within this, each 1 byte payload values are shaded between 0 to 255 to the image. So you can see on the right hand side, the bottom part, for each particular application. I mean, in this case, for testing, we use the internet popular applications like web and then other type of applications for the testing. And for each application, well-known applications, we can generate certain the matching images, as you can see at the bottom of the this slide on the right side. Okay, let's move on to the next one. So there's two phases. One is model training phase and validation phase. And for the model training phase, we first generate the payload image, and then our developed CNN classifier, we train them, and then in order to make it more optimized result, we perform the hyperparameter optimization, and then we repeat this until reach to the optimal status that we planned. And then once we have this the CNN classifier, optimized CNN classifier, where we input the not trained payload image into the our saved CNN classifier, and then produce the validation result, whether this is a good message or attacked message. And could you move on to the next slide? So in order to select the optimization set, the hyperparameter combinations, there's 5 different criteria, like convolution activation function, and convolution filter size, and pooling and padding, and fully connected activation function, and number of hidden nodes. And out of 1440 hyperparameter combinations, we chose those bold-faced boxes for the functions like ReLU and the size, filter size, the 7 by 7, and etc. So these are the result of hyperparameter optimization process. Okay. Yeah. Next slide, please. So this is a little bit different presentation of the how we run the CNN model. optimization set I already explained in the previous slide, and then from payload image to convolution and feature map, generating feature map, and then pulled feature maps, and then classification result, etc. These are the process we concluded and chose and concluded. Yeah. Please move on to the next slide. So this slide also shows we have two convolution layer and then fully connected layer for how to test and validate the convoluted images to verify them. So you can see that from the convolution process, we extract feature map from training data, and using the ReLU, and we use activation function, which can be applied to feature maps. And through the maxfull process, we extract the largest value from the feature map. And then lastly, softmax process functions for multiple identification. That's the process we went through. Okay. Next slide, please. This is our the current result based on the solution that I explained in the previous slides. We use the 1000 data, and we also performed the 1000 train steps, and we got accuracy of 97.3, and the precision and recall, you can see the numbers here. For this testing, we use the internet applications, about 10 popular internet applications. We haven't applied our the status message control and then status message between RCB and the control center yet. We are going to perform the testing and the validation based on the actual data, the control and the status message data between RCB and control center, because so far we spent most of our time to develop and implement the vehicle, RCB vehicle, and then control center. And then we also developed this SANA algorithm in parallel without having the actual data set yet. So now we are at the stage that we can test the real data based on the algorithm that algorithm and the solution that I explained it. So hopefully we can provide more detailed information in the next opportunity, whether on another OEM workshop or other the project meeting. Okay, I think that's about it from the CyberAttack solution side. Okay, thank you, Dr. Choi.
Okay. So this is the all for our site, and any questions, then we are open for your questions.
Yes, so you have questions from Jonathan here in the question and answer. If you can check.
Okay.
About the payload is a message.
Okay, so Dr. Tae-sang Choi, can you answer the questions? So the payload is a message. So
where is a question? You mean can we see the
Yeah.
question from the chatting window?
Right. Chatting window. So Q&A. So there is a questions from
now
the
it's in the chat.
Okay.
Now it's in the chat.
Yeah. Okay. So I see.
Mm-hmm.
Okay. Yeah. Doesn't seem to be a question, but seem to be comment that says the question is that the audience also tried a similar approach, converting from payload, which is a message, into an image, and they got relatively random on image. But from our result, it seems that we have a pretty we have nice patterns. Okay, how do you convert payload to image? In the slide, let me see. Could you go back to the here? So we use the we first when we collect packets, we collect packets in the unit of flow. So flow in the IP network, when we use the when we define the term flow, typically we use the 5 tuple or multiple tuples of the header parameters. For example, source and destination address, and then port numbers, and etc. And we also use the based on this flow definition, we first extract a set of packets into a flow, and then if you have n number of packets for a flow, then we remove all the headers and then extract payload part of those packets and combine them, and then we extract up to 784 bytes. The reason why we use this is we use the we want to convert that into MNIST database based image, and then for each byte, then we convert that into value between 0 to 255, and then we generate image. So since we are using this process, the result cannot be random. I mean, for particular application, for example, if we extract the web application, then a web application has a common characteristics up to this number of bytes, and when we generate image for those flows, we always we always receive this the same image result, so that it can be matched to that particular application rather than random. I'm not sure whether that answers your question.
Okay. Thanks. I don't know if Jonathan from the chat, if you received the answer that you are expecting. If not, we can go through the contact with the project and go for more discussions and clarifications. Okay.
Yeah. Of course, we can interact with any further detailed question and answers, Q&As later on.
Thank you. Okay.
Okay.
This is something that we have clear, is that to share between the partners, not only for the consortiums outside, and this is the idea for this workshop. Perfect. Thanks from the Korean partners. Thanks for the extra effort, and we know that you have now, I think that you are at 10:24, not?
No, 11,
11:24, different time zone. Okay, thanks for the effort. Sorry.
No.
Okay,
It's okay.
let's
Thank
see
you.
now. Okay, thank you.
Thank you.
And now it's time to go with a time break. That we can go with extra 5 minutes. And during this time break, only to remember to all the attendees that continue here connected, is that for the project we have a specific YouTube channel with all these videos and outcomes that we are producing. If you want to see Caramel in action, please visit. And another thing is that we build automotive threat modeling tutorial that now we will provide through the chat the different two links, the YouTube channel and the threat modeling tutorial. And if you want to check, you can download and you can go in some immersion in this process, in this case of automotive. It's an example that we as a project provide for everyone in an open way. Okay, see you in 10 minutes, okay, to follow the agenda. Okay, let's continue with this second workshop of Caramel project, Caramel in action. Okay, all the panelists are connected. The attendees maintain, perfect, near 40 connected. Okay, following the agenda now, after this time break, we will go with the rest of the pillars of the project. The next presentation that Jordi Casademont.
Yes.
And after that, Bob Elder from Green Flags. Okay, Jordi, the floor is yours. Stop sharing.
Let's see if I can share my PowerPoint. Okay. So can you see it? Yeah.
Yes. Only that the if you want to present is now not in presentation.
Okay. Perfect. Yes, in presentation mode. Okay. So hello. Good afternoon. Just going to present pillar 2. Pillar 1 was devoted basically to the sensors inside the car. Now we are going to see how the cars can communicate between them. We will have different radio technologies to communicate between them, and this will bring more attack vectors. Okay, more possibilities to attack our systems, and we need to detect these attacks and also to mitigate them. Okay, so let's see our approach. So in order to explain this pillar, I will introduce first of all a little bit this environment of the connected vehicle, and then how is our approach? Okay, the architecture that we have developed in Caramel. We will see that this architecture can be attacked. I will show which measures we have taken and which use cases we have designed in order to test that and to show these attacks, how they are implemented and how they are mitigated. So finally, some conclusions. Well, about this connected vehicle scenario, at present we have, or what we see, or what we envisage is several vehicles that are able to connect to all the different elements in the environment. Other vehicles, bicycles, pedestrians, all these kind of vulnerable road users, and also to the infrastructure. We will have several base stations or roadside units that are able to connect with. With that, we foresee different kinds of services, very nice services, very interesting services in the range of safety and also with the scope of traffic management. We can think about collision warning, platooning, lane merging, etc. Okay. In order to do that, we need some infrastructure. So what we have is in the car, we have the onboard units, and in the infrastructure, we have what we call the roadside units. Over these radio technologies, we also will have some protocol architectures. We need some security in order to authenticate, to encrypt all these messages. So we also need this platform that kind of protect the messages. Well, looking for the protocol architecture, in fact, we have a new stack, a new protocol communications stack, which is different from the one that we know of the internet, the TCP/IP stack. Here we have applications.
Sorry, Jordi, but we are not seeing the slides, only the first.
Okay, moment. Let me. Now can see something else.
Now connected vehicle.
Connected vehicle. Yes. Well,
communications.
Yes. Well, maybe now.
Now
it's in presentation mode.
Yes.
Okay. I don't know what if I share only the window of PowerPoint, it seems that it fails. But if I share everything, it works. Well,
Okay.
so, okay, fantastic. So I was saying that we have this new protocol architecture that we have, in fact, different protocol architectures depending on the continent. For instance, in Europe, we have the geo networking that it has been defined by the ETSI. In the United States area, we have the WAVE. There are other architecture protocols in also in Japan or in Korea. And well, as this is an European project, we are going to deal with the geo-networking architecture. Apart from that, all of these different architecture, they deal with different radio access technologies. So it means that the cars will have these radio communication facilities. The first one is one that we already have had for several times. That is that the cars, several cars, okay, are provided with one cellular connection, what we call one LTE UU in technical speaking. Okay, this channel is basic in order to, for instance, to perform emergency calls or to download upgrades of the car's software, etc. So we can take advantage of this link. For instance, in order to connect to internet services or to the PKI servers in order to provide all the security of our system. Nevertheless, on which we are really interested is in communications between vehicles, vehicle to vehicle or vehicle to vulnerable road users. Okay, in this way, vehicles connect between themselves and the delay that they suffer, this connection suffer, it's much lesser than the delay that we can have doing or using the cellular network. So in order to do these V2V connections, we have a couple of fighting technologies, meaning that they are fighting between them in order to be chosen by the industry. For one part, we have one technology that comes from the Wi-Fi, from the IEEE, which is called 802.11p. Okay, it appeared quite some time ago in 2010, and it's very simple. It's basic in the algorithm used with the Wi-Fi. And on the other hand, a little later, at late, or let's say 2017, it appeared one variation of the LTE, which is called LTE V2X. Okay, so here we have these two different technologies, but this one nowadays is still a little hard to find in a commercial way. Okay, so if you want to buy some cards, they are difficult to find. So for our testbed, what we have done, it has been using only the 11p. So we suppose for our testbed and our first implementations that in our scenario, we will have cars, vehicles, that they will be able to communicate between them. But there are others that they are not provided with this infrastructure, that they only have the, let's say, the standard cellular communication. So our main problem is that if the same area we have both types of vehicles, we need to communicate between them. We need that all the messages that are transmitted in order to produce these safety services are seen not only for the vehicles that are of the same technology that use V2V, but they are also seen by the other ones. Okay, so the first thing that we need is a kind of interoperability between technologies. And this will be even more complicated because in a near future, we will have new technologies. For instance, the IEEE is still developing a new standard, the 11BD, and the 3GPP, it has already standardized what we call the new radio V2X. Okay, this is the 4th generation, and now we already have the 5th generation. So in a near future, we will have different kinds of technologies, different kinds of cars working with these technologies that we need to operate between them. Well, this is just one phase of the problem, okay? Because the other phase is the security. So what is the approach, or how we have foreseen this architecture in Caramel? Let's begin with the side of the car. Okay, in the car, what we have is one onboard unit. okay, the OBU, that we call, with this, let's say, one processor, some memory, and with these two interfaces. There will be cards with a single interface and cards with both interfaces, the 11P and the LTE. Apart of that, as I said before, we relay in one security architecture based on PKI. So we will need some kind of certificates with keys, private and public keys, and these keys are quite sensitive. So the private ones need to be stored in a secure place. So what we have done is that in the OBU, we have deployed one hardware security module, okay, that is anti-tampering and prevents any physical attack trying to stall these keys. Well, so this is the basic OBU, but these OBUs are quite, let's say, quite standard. But our approach will be to introduce this anti-hacking device that you already have seen in Pillar 1. Okay, so we can leverage the fact that we already have one anti-hacking device for performing all these tasks with the image processing and the LiDAR and the noises in the Pillar 1, okay, with more functionalities. So here, connected to the OBU, we have the anti-hacking device that is able to perform additional security functions. This anti-hacking device is also connected to the canvas and can, well, basically take data from the canvas. Well, so this is in the car. Later, we will see which are these additional security functions. And what we have in the infrastructure, well, in the infrastructure, it's a basic, let's say, V2X infrastructure, which contains the radiating elements, the roadside units, the small cells in the case of LTE. Then what we have is the public key infrastructure to provide all these certificates. I also am going to explain a little bit how it works. And the new element that we propose to use is this multi-access edge computing. Okay, so what we see is that we will need some computation power in the infrastructure in order to provide these additional security functionalities. So we propose to use this MEC using the standard MEC framework provided by the ETSI. And inside the MEC, what we will have is, first of all, we are trying to move the communication protocol stack that usually runs in the roadside units to the MEC. So the roadside units and the small cells, the only thing that they are is a kind of radio bridge. Okay, so they take the packets from the cars, they translate them to one, let's say in this case, one Ethernet, and forward them to the MEC. And it's the MEC which is able to decode them to take the payload, to make the checking of the digital signature, to authenticate them, and so on. Okay, so in this case, the roadside units are simply in a radio infrastructure, but without any, let's say, computation needs. So they can be quite simple. Okay. Also, the MEC, it will be used for the interoperability. As the MEC is receiving all the messages, we can perform this interoperability functionalities. And then I'm going to introduce another feature that we propose, and it's quite new. It's the distribution of revoked certificates. Okay, just allow me to explain that a little later. So let's go first of all about the functions of interoperability. This is the case, for instance, that we have one region with V2V communication, or with cars that are provided with this 11P. Okay, so then so they can interchange this kind of V2X messages just to, let's say, to prevent collisions or to perform collision avoidance. And the main problem is that the LTE only car, the green car, is not receiving this message. So what we are going to do is basically this message is received by the roadside unit, forwarded to the MEC, and here in the MEC, using some forwarding rules that can apply filters. The forwarding rules can be based on region of interest, the age of the message, the type of vehicle. Okay, so here in the forwarding rules, we can set whatever we want. So let's say that in this case, we designed that all the cars in this region need to receive this message. So we forward the message using the other technology, in this case, the LTE technology, and this message reaches the green car. Moreover, it is also possible to forward this message to other regions. Okay, so imagine that this other region, it's let's say 500 meters forward, and the radio coverage is not so powerful, and it doesn't reach this region. So we are able to forward messages to any other region. Okay, so this is one issue about interoperability. Let's see the concept or the system in order to sign all the messages. This PKI infrastructure that I was telling before, okay, this architecture that you have here is in fact already standardized by the ETSI. The only thing is that there is not commercial products that are able to supply this. And in this case, in the Caramel project, we have deployed all the different software elements, okay, to run and to execute this PKI infrastructure. It works like that. I will explain a little bit how it works because it's interesting later for the rest of the use cases. In this case, what we have is, that the car, let's say, we have a couple of servers, okay? These servers should be provided, let's say, by one government. It should be provided by the regional authority, because all the cars that are sold to drivers need to be registered inside this infrastructure. So when the manufacturer of the car sells one car, what it does is to just assign one identifier to the car. It assigns what we call one bootstrap certificate, and also registers this car with what we call the enrollment authority. So the car is already it's already inside the system. So when the car starts for the first time, what it needs is to register to the system. So it sends the bootstrap certificate to the enrollment authority. The enrollment authority checks that this is a valid car, and then issues to the car what we call one enrollment credential. The enrollment credential is just one identifier, but without the identification of the car. This is something that provides privacy to the driver and to the vehicle. It's just one certificate that it says, I am an authorized car to be in the system, but I don't say who I am. So with this enrollment credential, I'm going to use another server, the authorization authority, okay, in order to acquire, let's say, a bunch of what we call authorization tickets. The authorization ticket is basically different certificates, and inside each certificate there is a public and a private key. So I am given, or the car is given, with all these certificates, and it will use these certificates to digitally sign the messages that it transmits. So, for instance, this car it's transmitting one V2X message with its position, its speed, the heating, and so on. All these driving parameters. And it takes this message, and using one of those authorization tickets, which one? Well, just one, okay, random one. It uses the public, let's say, the private key to digitally sign this message, and it will send this. It will transmit this message. So the cars that receive this message will check the message with this digital signature, and what is more is that this digital signature, or let's say that the certificate with which it has been signed, all these authorization tickets have been already also signed by the root authority. So all the cars will trust these let's say these digital certificates with which the other ones are transmitted? Well, so basically what we have is that all the cars using these authorization tickets are signing all transmitted messages. And here we have a couple of issues. The first issue is that what happens about privacy, because if I am using the same certificate during match time, okay, one possible attacker can see my route, can follow the places where I go. So if I want to improve the privacy, what I need to do is to change from time to time to change this authorization ticket. So in this way, I will prevent, okay, this spoofer from following me. Well, with that, now the main issue is, when do I change this authorization ticket? And this is one issue that we have addressed in Caramel. Okay, we have performed one algorithm that, depending on the number of remaining authorization tickets that I have not used, and also about the number of cars that I have around me, it computes when is the best moment in order to change the authorization ticket. And then another thing that you can see here is that, well, now we are going to see which attacks can suffer the different vehicles. But when one of these vehicles is attacked, okay, so it cannot be trusted anymore. So what we need to do is try to revoke the certificates that it already has inside the vehicle, that this car has already downloaded, because this bunch of authorization tickets remaining in the car, okay, are still not used, but should be revoked in some way, okay, because the car has been attacked. Well, so what we have done is that in some way, I will explain it later, in some way we will trigger one alarm, and these certificates will be revoked. So what we need to do is to distribute what we call one certificate revocation list. Okay, so we have one revocation authority which is informed about which certificates need to be revoked, and then we build this list and we distribute this list between all the different vehicles in the area. Well, so this is the other aspect, the aspect of the PKI infrastructure. Well, these open problems that we face when we have this architecture, one is the privacy aspect that I have already talked about, and then which are the different attacks that we can suffer. The first one is that we have in mind that the different cars, the different vehicles are continuously transmitting its position. This position is obtained by the GPS inside the car. And if this GPS is in some way spoofed, this vehicle will be transmitting one erroneous position. And this would be very critical because the car is saying that is in one place, which it is not. So we have to address this GPS spoofing attack. The other way, or the other attack vector, is what happens if we have some kind of transmission attack. These V2X messages also can be attacked. We are going to see that. And finally, the other attack is when some malicious attackant is trying to tamper, to open the OBU in some way. Could be hardware or could be software. So we also need to protect the equipment that is in the car, the OBU. Okay. Well, the countermeasures will be detect the attack and revoke the certificates. So let's see. These are the different problems that we have, the different attack vectors. Let's see the use cases that we are going to demonstrate in our testbed. So the first issue that we want to demonstrate is the GPS spoofing attack. As I said before, the GPS spoofing is, for instance, here we have a picture. One car is getting a good GPS reception, and suddenly we can have one drone that begins to transmit fake GPS signals trying to impersonate the satellites. So this vehicle will begin to receive this information and will compute one false, one erroneous GPS position. So in order to cope with that, we have two different versions. The first option is try to detect this spoofing inside the car. So inside the anti-hacking device, which is connected to the sensors of the car, using, for instance, the accelerometers of the car, the steering angle, okay, of the wheel, different or even cellular networks, from which we can obtain a kind of triangulation. The car can detect that it is in a position which is not the one, okay, required or acquired with the GPS. So we can detect this spoofing attack inside the vehicle. And the second option will be to perform this detection inside the mech. Okay, so as you remember, the mech receives all the messages from the surrounding cars. And these cars, these vehicles, would be able, in a feature, okay, to transmit the different detected objects. We have not talked about that, but inside the V2X messages, there are of different kinds. The basic one is the one that transmits the position, but then we have other messages that are able to transmit the objects detected by the sensors of the car. So if the mech receives the different positions of the vehicles and the objects that they are perceiving, okay, that they can build one global map of all the different vehicles, and matching the GPS position sent by the cars and looking the global map, they could be able to detect this spoofing attack. So once the spoofing attack is detected, then we can decide if we revoke the certificates of the car or not. But the first issue would be to detect it. Then we have the possible attacks to the V2X message transmission. Okay, so there are three different attacks that we have foreseen. First of all, would be one car that is using one false certificate. So this is basically to check if the PKI architecture and the building of the certificates is good. So basically what we do is to transmit messages with false certificates. And in this case, the different receiving vehicles will check the message, and basically they will drop the message. Also, these messages will be forwarded to the mech, and in this case, it's the mech who needs to check the message and also to drop the message. So this is one possible attack. Another possible attack is a kind of attacker that sniffs one message and tries to replay it, let's say, sometime later. So we need some algorithms to detect these replayed messages, looking for duplications or for the age of the message, and then just drop these messages. Okay, if they see that the message it's replayed, then we can drop that. And finally, the other attack is try to supplant some identity. So when one vehicle is transmitting its information, in the header of these messages, it states the kind of vehicle that is. For instance, it could be one standard vehicle, one car, one truck, one emergency vehicle, one bicycle. Okay, we have all these different types of cars. Well, so if one car transmits one message saying that is another type of vehicle, we need to detect that. Okay, and this kind of information is already stated inside the certificate. Okay, whenever one vehicle acquires one authorization ticket, this authorization ticket is valid for one type of car, the type of car that this vehicle has been registered inside the system. So whenever, if the vehicle is trying to send some information, okay, in supplanting some identity, then the system will also detect this fact. What else? Well, after that, we have the use case 3 will be one OBU tamper attack. Okay, we have one OBU, which is tamper-proof. We have performed different, let's say, hardware techniques in order to prevent that somebody is able to, let's say, to connect to the wires inside the OBU, or also one alarm that triggers when somebody opens the case of the OBU. Also software attacks. If somebody is trying to change the operating system or trying to change the software of the OBU, this is detected. So whenever one of these attacks is produced, then the OBU also produces one alarm trigger, and this alarm trigger is sent to the MEC, which is the one in charge of deciding if this attack is critical or is not critical in order to perform the revocation of the certificates. Well, so these are the three use cases with the three different possible attacks. And well, this is what I was saying. Whenever the vehicle detects that is under attack, it will inform to the MEC. The MEC will decide if the certificates have to be revoked. And then in affirmative case, if these certificates need to be revoked, then we revoke that. The main problem about performing this distribution of revoked certificated lists is the scalability. Okay, so if you have many cars that need to be revoked, and you also have many cars in the area, this list could be huge. Okay, so in Caramel, we have used one technique that is based in Bloom filters that in some way compress a lot these lists, and it makes that scalable for one region. Well, so this is the basics of the Pillar 2. As a conclusions, we can see that these V2X communications are already here. Manufacturers are already supplying cars with 11P. Okay, and we have detected all these possible attacks in the OBU and the GPS spoofing, and also in the V2X transmission. And our solution lays into two different devices. The MEC that is able to compute and to perform these functionalities that I have just explained, and the anti-hacking device that is inside the car. Okay, so with these two devices, we think that we can increase a lot the security of this environment, the V2X communication environment in the car. Okay, so this is all. If we have some questions, that I see that maybe we have a couple of questions there.
Yes, you have two questions.
Yes, a couple of questions. Have you done DSLC? No, at this moment, we have done basically 11P with LTE UU. Okay, the V2X, the V2V communications between cars, it's only with 802.11p. And the other cars have only cellular communication. So we can communicate them. In fact, not inside Caramel, but we are working also with this issue. The main problem is to have, let's say, CV2X interfaces, PC5, okay, let's say PC5 radio interfaces. We are working on that. It will not be presented in this project, but we want to use the same infrastructure, okay, to upgrade that to the PC5. Make slide 8. Let me go to slide 8. No, well, this MEC PKI maybe is a misunderstanding. There is inside the MEC, there is one client which deals with the certificate revocation list distribution. Okay, so the only thing that the MEC performs is the decision if this vehicle needs to have the certificates revoked, and this information is stored in the revocation authority in the PKI servers part, and then the distribution, the way in which this is distributed is inside the PKI. Okay, this would be outside of the PKI servers. Okay, because this is not standardized on how this CRL is distributed. Okay. Isn't your MEC proposal the same as? Yes, could be. Okay, it's the same idea. Okay, to have one MEC, but the only thing is that the procedures that run inside the MEC, okay, they are not standardized. We have this device, okay, and we can perform security functionalities inside it. Okay, so the approach is the same. Okay. How do you set the risks of the way? Yes, the Bloom filters have this drawback of false positives. In fact, I don't know here. This is one topic that has been designed by Atos. I don't know if we have Rodrigo in the call. Also, does your approach can detect similar attacks? Well, I cannot answer that. Maybe Atos is somebody from Atos in the call.
But Atos is not present, but we can go, with an answer in offline mode. Yes.
Okay. So, Roshan, we will forward your question, okay, to the people from Atos, and I'm sure that they will be able to answer your question. But yes, one of the problems that we have is the false positives. And in this case, well, we have to deal with that. Okay, so if you have further questions for this pillar, you can forward them to Natalia. That she's the coordinator inside, well, the coordinator of the different partners, and she will know to which partner involved in Pillar 2, this question needs to be forwarded to. Okay, so thanks a lot.
Okay, thanks, Jordi. And some questions appear. Perfect. This is the way to go in a workshop. And let's go with the last pillar. Green flux.
Yes. Good afternoon, everyone. Can you hear me?
Yeah.
Perfect. Let me share my screen with you. One moment. So can you all see my screen?
Yeah. Now in presentation.
All right. Thank you very much for the introduction, Jordi. And thanks to everyone for joining today's second OEM workshop. For joining the second OEM security workshop hosted by the Caramel partners. My name is Bob Elders. I work at Greenflux as a project manager, and we have provided use cases for the electromobility pillar. And in this presentation, I want to tell you a bit more about on EV charging infrastructure, possible threats, and how we work together in Caramel on countermeasures for this. I want to start with a couple of news articles that I found on the internet since the last workshop. So in my previous presentation, back in May, I started with some articles on the vulnerability of power grids, since those were highly relevant for the use cases that I described back then. But this time I want to share some news articles on the security of EV charging infrastructure. Because since the previous workshop, so since May, I believe, a number of security leaks have been found in EV charging stations. Fortunately, these leaks have been found by professional penetration test companies, and the impact is not that big, but it shows the relevance of the Caramel project even more. And hopefully after this presentation, it will be clear to you how it was possible that these security leaks were found at all, and why it is also not always possible to fix these issues. But that we might be able to detect them remotely and take counter or to take countermeasures or to develop mitigation techniques. So during the previous workshop, I gave a high-level explanation on the use case, why cyber attacks have impact on power grids, and I gave a high-level explanation on the machine learning pipeline that was developed for this project. Today, I want to go into a bit more detail into the technology itself. So what is the main communication protocol that is used? What does the communication architecture look like? I want to share some preliminary anomaly detection results with you. And I want to talk with you about the deployment of the machine learning pipeline. But first, I want to do a quick recap of the EV charging ecosystem and its main players, such that we have a common starting ground. So let's go ahead. Yeah. So in the EV charging ecosystem, we distinguish two roles, basically. So on the one side, we have the MSP or e-mobility service providers, and they offer EV charging services to their customers. So they provide access to charging stations, usually by providing charge cards to their customers or to EV drivers. And on the other hand, there's the CPO. So those are the charge point operators, and they are responsible for the installation, operation, and maintenance of the charge stations. And some parties, they fulfill both the role of EMSP and CPO, but mostly these roles are fulfilled by separate parties. So where do we as Greenflux come in? So we offer a wide label CPO and EMSP platform, and we allow our customers to run their CPO or their EMSP business to run that efficiently. So we are not a CPO or EMSP ourselves, but we only provide the technology for these parties. And to give an even higher overview of the EV charging ecosystem, let's zoom out a bit further. So this overview shows the actors in the EV charging ecosystem or EV charging landscape and how they interact with each other. So it shows where we have data flows, where there is energy transfer, where there are only temporary data exchanges between which actors. And we also within the Caramel project investigated where attack vectors are located, and I will show them to you. They're basically located everywhere. And lack of security at EV charge stations could cause problems for users, but also for charge stations and for central systems or the systems that are operated by the CPOs. And it's therefore important to know how to identify these attack vectors, and we can classify them in two different categories. So on the one hand, we have the physical aspects, so that's hardware. So that's physical breakage of charge stations, tampering with charge stations. And next to that, we have the aspects related to information technology. So that's basically the link between charge stations and the backend system. And here we can find protocols that are not secure, for instance, HTTP, or other services such as mobile phones, where during the data exchange or data communication, data could be tapped and information could be obtained illicitly. So there are certain vulnerabilities that could be exploited through a series of attack vectors, and that can cause problems at the charge stations. And among the attacks that would compromise this type of infrastructure, the charge stations, we have brute force attacks, we have SQL injections, one could attack unencrypted communication channels, things like that. But almost all attacks, they either impact the EV, so that's the electric vehicle, or they impact the charge station. And by applying machine learning tools in the CPO cloud, we can try to detect and mitigate these attacks remotely, all from a single tool. So the communication that we are interested in it's running here. So it's between the charge station and the central system. And the machine learning tool that is developed to detect anomalies, it runs here in the cloud, in the cloud of the central system that is running in the cloud. And the advantage of having a machine learning tool running in the cloud, running at the back office, is that it is hardware agnostic. So it doesn't really matter which type of hardware is used. The machine learning tool can respond to any type of hardware that's being used, and that's a big advantage because in Europe alone there are dozens of charge station manufacturers, and each of these charge station manufacturers has its own security issues. And by developing a tool that runs in the cloud, we can use only a single tool for all these different manufacturers. And machine learning tools, they rely on the availability of large amounts of data. And despite the fact that the data consumption of a single charge station should be below 10 megabytes a month, there is quite some data traffic going on between a charge station and a central system. And all this communication takes place according to the OCPP communication protocol. This also means that all the data that is available is limited to what is prescribed in the OCPP description or the documentation. So now we have a basic understanding of the EV charging landscape. Let's investigate this OCPP protocol a bit further. So starting with the communication between the charge station and central system. For those of you that are familiar with the OSI model, OCPP works on the application level. So a connection is established between a charge station and a central system, and here the central system acts as a WebSocket server, and the charge station acts as a client. And the implementation can be done using either JSON or SOAP communication. And OCPP describes all the communication between the charge station and the central system. So everything that's happening here, it's all according to OCPP. But the central system can take other inputs. For instance, from energy utilities, they may communicate to the central system how much capacity there is available on transformer level in some local area. And of course, on the other side, there is the EV that is physically connected to the charge station, and where there is also energy transfer and communication between the EV and the charge station. So secure communication and operation is a critical aspect of EV charging infrastructure. And in the latest version of OCPP, so that's version 2.0.1, security features such as secure communication setup and secure firmware updates, messages like that, they have been added to the specification. But at this moment in time, only a handful of charge stations, they actually support OCPP version 2.0.1. And the majority of the charge stations, they are connected using OCPP 1.5 or OCPP 1.6. And these versions of the protocol, they do not have these security features. Also, many of the charge stations that are currently connected to our system or to any system at all, they use hardware that is maybe 10 years old. for these legacy charge stations, it's not always possible to update the firmware, and therefore it's not always possible to update the communication protocol that they're using to communicate. Which means that we cannot also not update security measures on the charge station itself. And this also underlines the importance of the Caramel project, and it is to develop security tools that can also be used on these legacy chargers or legacy hardware. So what type of OCPP messages do we have? Let's investigate it a bit further. So since version OCPP 1.6, we have a set of command stages. That's what OCPP calls these messages, and we have them in 3 categories. So we have messages that are used during startup and initial configuration. Then we have transactions and control messages. So that's everything, all messages related to a single charging session. And finally, there are the notifications and the maintenance messages. So those include messages to get diagnostics from a charge station or to perform firmware updates, messages like that. But from the messages, if we inspect these, we see that OCPP relies on the security that's provided by lower level communication. So that's, for instance, TLS on the transport layer, or the WebSocket security. But there's no security of OCPP itself for OCPP 1.6. So it only suggests to apply TLS or an SSL for the critical data that's being transferred between charge station and the central system, and the other way around. But it does not explore any of the security measures. It doesn't explore any security measures to manage the communication. But what are the threats that we are facing here? So within this project, we have done some investigation what the possible threat scenarios are, and we have specified 3 different categories. So one is information disclosure. So this could be illegal or illicit reading or copying of data. So this could, for instance, mean that someone is able to copy authentication ID of another EV driver. Then there is the elimination of data packages. So this may generate a denial of service situation. And finally, there is distortion. And distortion of information, we think that's the one with the highest impact. Because distortion of OCPP messages, it could lead to disruption. So could lead to denial of power services. It's possible for someone to steal energy if he's able to distort these messages in some way. So to illicitly obtain power from a charging station, or maybe to interfere with dynamic pricing. And finally, there's the overload. So creating variations in power levels on charge stations may cause overload in local power grids, which in turn may lead to local blackouts. So yeah, clearly distortion is the threat with the highest impact. So let's have a close look at these OCPP messages. OCPP 1.5 consists of 24 different message types. OCPP 1.6 is a bit more advanced. It has 28 different message types. But if we look in the logs of our server, we see that about 75% of the messages comes from 2 different, or actually 3 different message types. So those are meter values, which are basically the measurements coming in from the charge stations, and we have notifications on start and stop transactions, which make up for about 20% of the traffic on our server. And the remaining 25%, it's made up of all the other message types. And these are not sent with every transaction or not sent at regular data intervals. So for this reason, we've chosen to build a machine learning tool that is using only meter values and start and stop transaction messages as input. But before we can feed these messages into the machine learning tool, they must first be processed. So messages in OCP 1.5, they have a different format than messages in OCP 1.6. So messages, they have a SOAP format, others have a JSON format. So we have to do some pre-processing. And I want to explain to you how we do this on a higher level. So I already shared or already showed you this image, a similar image as this one during the previous workshop with you, but this one goes into a bit more detail. So charge stations, they can connect using a SIM via a private APN. So it means separated from the rest of the internet. And they can connect via the public internet. And if they connect through a SIM card, then all communication is going to the telecom provider first, and via a VPN tunnel, it's communicated to our socket server. So no matter what type of connection is used, all messages end up at the socket server. And we have separate socket servers in place for, well, what type of connection is being used. So whether it's private or public or SOAP or JSON or etc. And from here, messages are placed on service bus. Service bus, the Greenflux services. So we have internal services depending on what type of messages we receive that need to process these messages. They read these messages from the service bus, and they take further actions. So some services they create charge detail records. So those are basically summaries of charge sessions, write them in a database. They send bills to our customers, etc. Other services, they process the meter values that we receive, and they store them in a separate database. And depending on what type of data we receive, the data must be stored up to 7 years for depending on what type of data it is. So the final step before this data can be used as input for the anomaly detection tool or as training data is data anonymization. So due to GDPR restrictions, we cannot share this data directly with any tool. So data must be anonymized, and after this, it is sent to the anomaly detection tool to train. And the training is mostly done offline, or so far it has been done offline. And I would like to share with you some preliminary results of the anomaly detection tool. All right, so the data set that was used to train on, it contained about 4 million entries and consisted of data from different years. And the machine learning pipeline, and I already described this in the previous workshop a bit more in a bit more detail, consists of several parts. So we first have an unsupervised machine learning part, and after that we have a supervised machine learning part. So well, in total it's a semi-supervised machine learning pipeline. But for these different parts, so for the unsupervised machine learning part and for the supervised machine learning part, different kernels can be used. And depending on which kernel is used, sensitivity for anomalies may be higher, which means that more anomalies will be detected, but this will also lead to more false positives. And yeah, the sensitivity mainly depends on what type of kernel is being used here. And the training data is multidimensional. So this makes it a bit difficult to visualize any outliers. And therefore, we introduced the principal component analysis. So principal component analysis is used to observe or to visualize any outliers. So it allows data to be visualized in such a way that it's it's visually is easier for us humans to visually detect or to see the outliers. And with PCA, this is going a bit into details here, but the main components of the covariance matrix are calculated, and then the two most important ones, they are selected, and these are the two eigenvectors that are orthogonal to each other, and they will become the principal axis in a new visualization of the data. The main purpose of PCA is to extract a knowledge from the data set without losing any important information. And of course, it allows for better visualization, but let me explain that to you with an example. Maybe that's easier. So in this case, isolation forest was used for anomaly detection, and it was used on charge detail records. And charge detail records, they are summaries of charging sessions. So they tell us on which charge station a session took place, which user did the charge session, what the startup time was, what the end time was, what the duration was, how much energy was transferred, what the total cost of this charge session were, etc., etc. And isolation forest is used a lot for anomaly detection, and it assumes two things. It assumes that the anomalies are few, so it means that there are only a couple of anomalies in a large data set, and also that the attributes they are very different from other values. So it should be quite easy to detect anomalies that are really different from other entries in the data set using isolation forest. And as I said, this graph only shows two attributes. It shows, or two features. It shows volume and duration, but there are a lot more. So it's quite difficult for us to see what is exactly going on here. And through PCA, we can reduce the number of dimensions. So we reduce the number of dimensions to 2, and we plot the same data. So in this case, it's much easier for us to see what the anomalies are. And to detect where these outliers are located. In this case, they are located on the right side of the graph here. And there's actually a nice side effect that I would like to tell you. Back in 2018, we had a small bug in our software, which led to CDRs, which led to the costs of CDRs being calculated falsely. And these entries for some of the CDRs. And the anomaly detection tools were able to detect these falsely calculated CDRs. We're able to detect the bug based on this data. So that was working pretty well, actually. So much for the preliminary results. The next step will be the deployment of this tool, because so far everything has been done offline. The goal is, of course, to make this tool.
Sorry, Bob. Only 1 minute, 2 minutes to finish.
Oh,
okay.
This is the last slide, so I will speed it up. The goal is to make the tool work online, where live data is being fed to the tool. But the tool will be hosted on a remote server, and for this, a data connection must be established between in two directions, so from a platform to the tool. So what will this anomaly detection flow look like when the tool is deployed? So we have a charge station that can be located, for instance, in Paris, and it's talking OCPP to our platform that's hosted in Amsterdam. And our platform, so we do some data pre-processing. We send messages, we push the anonymized data to the machine learning tool that's hosted in Berlin via a push API. Then the tool that is running in Berlin, it runs every fixed time interval. So for instance, every 3 minutes or every 5 minutes, maybe every 15 minutes. If anomalies are detected, then it sends back notification via another API to our platform, back to our platform. And depending on this type of anomaly, depending on what the type of anomaly detection is, we then take the necessary mitigation action. For instance, we might disable the SIM card that is located in this charge station in Paris to make sure that no further harm can be done from there. We're still working on this. So if this pipeline is in place, then we should be able to detect anomalies depending on how often the tool in Berlin is running, but this may be within 15 minutes. And this is something that we are building currently. So hopefully in the next session, I can give you more. I can talk to you about the results from this. And this brings me also to the end of this presentation. This was a bit of a long minute, Jordi. I hope everybody has learned why these detection and mitigation techniques, why they are important, and if in the future we still want to be able to use the charging infrastructure that we have already placed in the field. So these legacy charge stations. So thanks for the attention, everyone. And if you have any questions, please let me know.
Yes, you have one question in questions and answer. It's about the,
yes.
You know, if you can see only.
I see a question from Jonathan. It's about which standard specify EV security, and what gaps do you think should have to be addressed? Okay, so I have to admit here that I unfortunately do not have any knowledge about the security of the EVs itself. So my knowledge goes all the way from the cloud platform all the way to the charge station, but that's basically all the knowledge I have. And the EV is located on the other side of the charge station, so to say. So unfortunately, I cannot help you with that. I think that the security it depends heavily on what the charge station manufacturer is, and I'm not sure if there is a fixed standard at the moment for EV security. I hope that answers your question. Then I will now stop sharing the screen.
Bob.
Thank you.
Okay, for all the presentations, you know, and the questions, please contact us through our website or info account that we will provide it at the end of the workshop, and we will be in contact. It's the idea for these activities. Okay, next stage for this workshop. Now it's time to be with the round table, and I'm checking, and okay, Alejandro and Jesus. Okay, let's go with this. This is the last activity for today and this workshop, and only to present who will be in this round table. Welcome to the new attendees, and thanks for maintaining that. It seems that all the content is interesting, and we are happy and glad for this. For today, this round table, we will put in gallery mode. Please, panelists, video on. You have to accept and to consent that you will be recorded. Okay. Pues we have the different. I think that it's missing Petrus. You can see my screen because we have today Jesus Alonso for the 5G PPP chair, and this is part of our Caramel Advisory Board. Hello, thank you for being here, Jesus.
Hello, Jordi. Thank you very much for inviting me today. Just to clarify that I am not the chair of the 5G PPP. I'm the chairman of a particular working group focused on 5G 4CAM, for connected automated mobility. So just to clarify this, I mean, the chair of 5G PPP is Colin Wilcock from Nokia, and I don't want to take over He's wrong.
No, no, it's not. But you know, in the same level.
No.
Okay. And for this, Christo is not. I don't have any new link. Christo seems that have some issues to enter, but it's something that we have to solve. And Alejandro Manilla from IDIADA. Hello.
Hello. Glad to participate.
Okay, perfect. Thanks, Alejandro. We are very happy to be that near OEMs and tier ones are present in this kind of activities. And from the project, Peter Hoffman, that you know, our Caramel Technical Coordinator from Dutch Telecom Security. Hello, Peter.
Hello.
And Petros Kapsalas is from Panasonic. This is the leader for Work Package 6, the trials work package that I think that is connected. Okay. And now for Christos, we will try to solve why he cannot be inside. And let's start basically for today and roundtable main topics. We will be with 3 blocks. The first, as you can see here, is about the, and following all these previous presentations from the project is the present and future SICAM main cyber threats. And the second is about if we want to be near the OEM and tier 1 partners, and we want to share with this the main vision and main insights for them. And at the end, about something that appear in some of the presentations about the privacy on SICAM or maybe the car privacy topic. Okay, this is the 3 blocks that we will cover. Now I will stop sharing. We can go, in this gallery view, and let's start with this round table. And more or less, there is no order to cover the different blocks of data. We have some minutes, 20 minutes, and we will go in a quick way. And for the first, about the cyber threats, we'll see more or less the present cyber threats detected in projects like Caramel for SICAM. And what do you think about this in the way of the present and basically for the future? I don't know, we can start with Alejandro, from IDIADA.
I was showing the previous slide that had been presented during today. I think that there are already some examples of cyber threats that we are going to suffer. So, for example, the GPS spoofing, these kind of attacks can be even more relevant at the moment that we are introducing autonomous vehicle functions that depends on the position and the positioning system for the work of these specific functions. And then imagine having this kind of GPS spoofing on something, on some vehicle that needs, and it's very relevant for them to use the GPS position. So we are speaking not only from a fake spoofing for the navigation, we are speaking about crashes or direct issues on the safety of the drivers and these vehicles in this case. I think all these connected features that we are introducing in the vehicles are the new spots and will be the future also of the cyber threats. We are adding Wi-Fi, we are adding Bluetooth, we have the GPS signals. Even we can see attacks right now in the tire pressure monitor systems, common attacks like the remote keyless entry system doing replay or jamming attacks on the radio frequency. All these that are remote vectors to the vehicle, not only the inside network of the vehicle, all that can be accessed from the external are the main points, the critical issues in cybersecurity and the ones that are going to be more affected right now. And obviously in the future, as we keep improving and introducing new technologies, like for example, we are seeing now vehicles also with NFC, and for sure there are going to come additional features with additional connectivity in the vehicles.
Okay, thanks, Alejandro. Here, Christos is present now as a panelist. What is what do you think about this? Future cyber threats and SICAM.
Okay, first of all, hello, everybody, and thank you for the invitation. The second is I just connected and I have lost some of the review, so please can you repeat the question?
Yes, basically is that for the roundtable now, we saw some of the present cyber threats detected by this project. And we are now thinking about your opinion about the feature, the missing, that now for this project, maybe we are not.
Okay. Let me say, because we work on the NIOV project, we make recently a survey and with a lot of stakeholders in order to clarify the immediate, let's say, needs in the cybersecurity. We talk with OEMs, we talk with, let's say, administrators of infrastructures or smart cities or so on. And I also saw your approach in Caramel, which is very interesting and covers for me a lot of things that we see. What I will say that we have put some challenges that they are, what you say first of all of the OEMs is that they basically, they scared, let's say, scared, two things. The first one is the communications, attacks on the communication, which is basically one of the things that we need. A second thing that it's also something that it's not very common, but if we go and we see that how the cars and the connected vehicles, not only the autonomous, generally the connected vehicles that behave with the infotainment and so on. And if we see, let's say, applications of autonomous vehicle that is major having to do with fleet management, or for example, public transportation or something like this, meaning that they are not cars for individual drivers, but mostly managed by an organization. It's one of the things that they are looking is the part of the malware and other, for example, ransomware attacks. There are not a lot of, let's say, components in the car that are able to have such attacks, but if we see attacks in infotainment system and so on, it's something that it's very crucial for them, because it's very possible to let's say cut off all the operation. And a third thing that it's very we have concluded is that they have the way of the security updates in the systems. How we can have real-time security updates, real-time diagnostics, how the vendors can provide such updates in the systems, how this can be done and when, because when you have a car, you cannot, for example, reboot the system, the OBU, so easily. It would have a problem. So from my point of view, apart from the things that you have already said it in your workshop, I had to add this, let's say, as some open issues that I believe that we have to see in the future, but in the near future.
Okay, thanks, Cristo. And Jesus, you know, is your vision for this?
Yeah, so essentially from the working group that I'm chairing in the context of the 5G PPP, for those who don't know, this is a program that has been funding projects in the area of to develop 5G in the European context. Many of these projects have been working on developing 5G, a tailored version of 5G for connected cars. So what I think the majority of these projects is doing essentially is putting the focus on developing the communication technology, but also the processing technology. And what we see in the future is that this processing technology is going to be distributed across many, many elements. So not only the cars, not only the sensors and actuators on the car, but also the infrastructure, the edge, the middle edge, and all the way up to the cloud. So what I think is that one of the challenges we have to face is how to provide protection in this huge surface. So sometimes the discussions about cybersecurity for mobility is very much focused around the vehicle, around the car, And I think that also we need to look at the entire chain where the data flows, So as we see data being generated and exchanged between cars and vulnerable road users, infrastructure, and many different elements in the network that belong to different players, this is challenging. Also, we see that in the future, we are talking a lot about Open RAN, where the networks are not going to be operated by one single player, by one operator, for example, working with one vendor, but we're going to see a lot of players playing together, interacting together to provide these services for autonomous and connected mobility. And here I see a huge challenge on how to protect all these enormous and very difficult to control surface attack.
Okay, thanks. And after this, external views that it's very useful for us. Here, Peter, Petros, what is your opinion? Because I think we are some remaining things that we can go with Caramel for the trials. For instance, that in this case, Christos, you talk about maybe ransomware in the car. No, maybe it's part of the threats, and see if some cars will be kidnapped. Not. It's like the computers that now we are suffering. Okay, what is your opinion of this vision, Peter, Petros?
Yeah, maybe to stress a few points beyond what we discussed today and what we actually did in the Caramel project. I'm talking from the perspective of a security company, security expert. And I've talked a lot about attacks on the interfaces of the car, on the communication systems, on the cloud systems. But I think there are quite a few aspects that maybe we can cover in future projects that also affect the security and safety of the car. For example, if I look at the software development process, when developing all these complex software systems that go into the car, that go into the cloud, and that somehow regulate the traffic and so on. Yeah, maybe an anecdote at one point, there was an estimate that Windows 7, I think, had 26,000 unknown bugs that could be exploited by an attacker. And the same software mechanisms, the same development environments are used to develop the systems in the car. Of course, there are some safety standards that vendors have to adhere to, but still, we are using basically the same technologies. We are using off-the-shelf embedded operating systems. And I think that's a problem. We don't really seem to be able to manage the complexity if you look at all the zero-day exploits that occur in the wild, and bugs that are under the hood for 10 years and they're not fixed and nobody knows about them. Maybe some bad actors know about them and can exploit them, and we don't know that. And these are deficiencies that, of course, a problem in the software industry in general, but when it comes to vehicles, when it comes to traffic control, it really becomes a danger to human life if you have something like that. And we need improvements in this area specifically. I know that there are some attempts to do add instrumentation to embedded operating systems so that an attacker, even if there are some bugs in the software stack, is not able to exploit them. Maybe it's detected that there's an attack is going on, and we have to concentrate on technologies like that. So that's the one hand. On the other hand, when you're looking at autonomous vehicles and maybe vendors are also using machine learning to implement functions of the autonomous vehicle. And we had some examples in the project how you can maybe exploit deficiencies in machine learning models. And yeah, that's also, I attended the workshop on CCCam ethics not too long ago. And I think one of the things that we have to address in the future is the question of explainability and transparency of machine learning algorithms when it comes to automated or assisted driving. And we must be able to have insights in how these algorithms work. It's not sufficient to take a huge set of data and do a training, and at the end, it seems that the car is doing what it's supposed to be, but you actually don't know what's going on behind the scenes. And I think that's a problem from an insurance viewpoint, from a legal viewpoint, from ethics viewpoint, and that is something that has to be addressed. Of course, that's a general problem for machine learning in all contexts. But as I said previously, when you're looking at human life, at the danger to human life when it comes to traffic, to vehicles, then it's especially urgent to address these topics. Maybe just my insights, a little bit forward-looking, beyond the project. Yeah.
Yes, Petros.
Yeah, so at first, thanks a lot for all the comments. I found it very, very helpful. And I think that they touch topics that we have been thinking in Caramel from the proposal phase until now. I will comment more from the sensing and from the automotive perspective, because this is my expertise. I have noted down some of the comments. I think that Christos mentioned that the OEMs are very skeptical about the attacks on the communication layer and how this will affect the safety, and also about the security updates and some possible malicious attacks on this layer. So the way of thinking in Caramel is that in the automotive and in ADAS, there was the traditional concept of redundancy, which said that it's not enough to understand the world by one sensor. You need to verify the conception by multiple sensors. And this topic, which was the traditional topic in ADAS, which was enforced by standards, I see this being adopted in autonomous driving as well. So, for example, it's not enough to know your location by the GPS, because the GPS can be spoofed, but the car is not only a node of the vehicle of things, but it extracts information on its own. So the location of the vehicle is not only known by the GPS and by the V2X, but you know it using your lidar odometries and your visual odometries and your vehicle odometries. So this is why in Caramel, in Pillar 1, I tried to explain the use of multimodality for the mitigation of the cyber attacks, because even in the case that the network is attacked or one sensor is attacked, you also have the other sensors to mitigate the attack. This, for me, this is a very critical topic, and I see that the community should preserve the modularity of the solutions for the forthcoming years in order to be able to control such attacks and mitigate it. This is my expectation, because otherwise, if we don't adopt this concept, I agree with all the concerns that were made so far, that there is a very huge challenge that we will fail. But so this is one of the basic reasons that in Caramel we try to get benefited by the multimodality of the perception. For the mitigation, for me also, one very critical topic in order to assess the safety of these systems is to come up with some KPIs. So far, I see that the community is just borrowing KPIs from perception, but we don't have yet, at least according to my understanding, KPIs that quantify the cyber attack severity and mitigation.
Okay, I think for this first round, it's okay. We cover the first two blocks about the cyber threats, the OEM vision, with some extra information. And if you agree on taking the time that we are and the attendees remaining, is that you know that there is a lot of challenges in the CCAM not to go ahead through different initiatives, projects with we want to imagine that OEMs tier 1, some of the kind of the partners that are now in Caramel, research, the technological center, universities, academia work together, is that if you have to see a main topic to be funded. What is this topic for you? We can start with Jesus, for instance.
Well, this is a very interesting and difficult question to answer.
No. Here is that for new proposals, you know.
No, I definitely think that what is important. Again, let me talk from my perspective. Okay, from the 5GPP is going to have continuation in the SNS, and the work programs are being developed and are being it's still being defined what is going to be funded. I definitely think that cybersecurity needs to have a more important role in this project. So definitely the definition of the beyond 5G vision and whatever 6G becomes must have cybersecurity by design. And I think it's very important that in all this process, we make sure that we involve the OEMs, the tier one, and everyone involved, all the users. So to make sure that we don't generate technology that does not take into account the real needs from those who really need to use this technology and make it a success. So I would say that anything related to cybersecurity, we need to ensure that is embedded into all the projects, essentially.
Okay, thanks, Jesus. And from IDIADA, Alejandro.
Yeah, at the end, I think cybersecurity is something that it's transversal. Okay, so in any project that requires a vehicle cybersecurity, it's not only an additional field. So cybersecurity, it's transversal to the development of all the project. We have the development phase, the production phase, and even the post-production phase. All the life cycle of the vehicle, it's important for cybersecurity. From the beginning to define risk assessment to identify the risk, to the moment to the production to be sure that the supply chain, everything is correct, and then also in post-production with monitoring activities, incident response. At the end, it's hard to say that cybersecurity is only an additional topic. Cybersecurity is transversal during all the life cycle of the vehicle's life, and then it's quite important, no? If you did say, okay, let's choose a topic or an additional topic that it's not only focused on the vehicle side, then we need to go also a step out and start to see what is the problem with the cybersecurity with the external side. So it's infrastructure. We are going to have right now, not yet, the vehicles are not capable yet, or still something in progress, but we are going to have a lot of communication V2X, vehicle to everything, vehicle to vehicle, vehicle to a smart traffic light, vehicle to, I don't know, whatever you think a vehicle can communicate to maybe support the autonomous vehicle functions and support the rest of the ways to establish communication with anything, no? So I think this also this additional point that is coming in the future, this hyper connectivity between everything. Cybersecurity is going to be not only relevant for the vehicle, also relevant for the environment of the vehicle, no? So I think it's something that is transversal right now for the vehicle and will be transversal later on for all the environment.
Okay, thanks. And Christos. Muted.
I'm losing my Zoom. So, yes, for me, I would like to say something that what Mr. Kapsala said, and that is very important, that to see the mitigation, the response to the mitigation processes that follow detection. In the OV project, we have some scenarios of responses, and to tell the truth that either by detecting or let's say try to taking some values, multi-values for value sensors in order to see if this is the correct value, for example, GNSS. We see that the most safe way right now is to have as a response action the stopping of the car. But this is not very easy thing, because it's not only the stopping of the car, it's the safe stopping of the car. Because if you stop a car in the middle of the road with traffic, then you have an accident. So I think that it's a very, very difficult task, this, because it has a lot of parameters to take into consideration. It's not only the ICT part or the hardware, it's the physical part of the environment, which is around the car, and so on. So I know, I totally agree with you that if we don't follow to this, we will have problems in the future. I think that there is a lot of good work in both academia and both in the security companies. In this way, we will have very good approaches in the near future about this, but if we don't see how we will have safety mitigation measures for such attack, then you are right, everything will go wrong.
Okay, and Petros.
Actually, the people who have spoken before me have already mentioned, I agree with what Alejandro mentioned, that also my view is that the problem needs to be solved not only on the node layer, that is the vehicle, but also on the system layer, that is the infrastructure plus the other traffic agents, because as Christos also mentioned, okay, let's say that you are able to detect the attack, but so which is the fallback action? If you don't have information from the system layer, what are you going to do? So I agree that we need to approach the solution as a solution that runs in the system of system layers. If you consider the car a system, then you need to go to a system of systems to solve it. And also, from my perspective, that I'm coming more from the sensing community, I think that in the sensing community, we don't have KPIs and we don't have any standard yet. While for the mobility pillar, the advances are more mature, they have advanced more. On the sensing pillar, we are on a more primitive stage. So I think that both the academia and the industry needs to move towards defining some KPIs for the quantification.
Okay, and Peter, for this last round.
Yeah, of course, I agree with all the points that have been made. Maybe one more quite concrete idea now when you're looking at the vehicle-to-X protocols, and maybe look at some recent experience in the last years with the Wi-Fi protocols WEP, WPA. There have been systemic errors in the protocol design that have been discovered quite late, when millions of devices have already been deployed and were affected by the bugs and attack vectors. And we should avoid that for vehicle-to-X communication, because it's much more sensitive than Wi-Fi routers. And as I said, people's lives at stake probably. And so maybe a concrete idea on a follow-up project would be a thorough security review of vehicle-to-X protocols and look at possible weaknesses, possible privacy issues, and try to fix them as soon as possible before it's widely deployed. That's my very concrete idea what should be done in the future.
Okay, thanks everyone. We got some ideas for now, for the present, for the rest of the projects. Thank you for your time. Thank you, Jesus, Alejandro, Cristo, Petrus, Peter, and see you in new activities. And from Caramel Project, remember, now it's the end of this workshop, this second workshop. We will have a third workshop, with results of the trials next year. We will be invited, we are sure of this, and taking account of the different comments of the different speakers and panelists. Only remember about our tutorial we shared with you. It was based in a strike model, taking in account not only the car, all the environment, and if you want to download, it's available in our website to go forward with this kind of things. Okay, see you next time. And we have good photos and screenshots for all the panelists that will be provided, you know, in some minutes. Okay, thanks. See you for next time. Nice Tuesday.
Bye-bye.
Okay.
Bye.
Bye.
Thank you very much.
Bye. Thank you.
Bye-bye.
Have a nice day.